Multiplying radicals. The product rule. The nth root of a times the nth root of b equals the nth root of a times b. To use this rule, they must have the same index in order to multiply. Example 1. For a, we have the square root of 2 times the square root of 7. So first, because we're being asked to multiply, check the index. Since they are both square roots, we can write them together and write it as a single radical. So we write it as the square root of 2 times 7. Notice there's no sets or pairs that can come out. So our final answer is square root 14. For b, we have the cube root of 15 times the cube root of x. Notice we are being asked to multiply, so they have to have the same index. Because they are both cube root, we can write it as a single radical. So we write it as the cube root of 15 times x. But we want to factor to make sure, to see what we're really dealing with. So 15 is made up of 3 times 5, and x cannot factor, so we leave it as 3 times 5 times x. We do this so all the factors are laid out before us to see if we can pull out any sets. Do we have any sets to pull out? No. So your final answer would be cube root of 15x. C. We have the square root of 3x cubed times the square root of 6x. Notice they have the same index, so we can write it as a single radical. So now we write it as the square root of 3x cubed times 6x. Now that they are under the same radical, we want to factor each piece individually. So notice 3 cannot factor, but x cubed really is x times x times x. Now we look at 6. 6 is made up of 2 times 3, and then x cannot factor. So now that we have all the factors laid before us, we want to organize it. We want to group all the like factors together. So we take a moment to rewrite it, and so now we see 2 times 3 times 3 times x times x times x times x. Now that everything's in factored form and organized, now we can clearly see any sets we may have. Because our index is a square root, we have to have pairs or 2 of the same thing. Notice we do have a pair of 3's, so a 3 can come out. Notice we have a pair of x's, so an x can come out. And we have another pair of x's, so another x can come out. But notice the 2 does not have a pair, so the 2 must remain under the radical. So although we've pulled out all the sets that we can, we need to simplify our answer. Instead of writing 3 times x, we write it as 3x squared square root 2. And that would be your final answer. For D, I have the cube root of 2 times the cube root of 32. Notice they do have the same index, so we can write it under a single radical. From here, just like before, we want to factor these values. So take a moment now to do the factor tree of 32 and list out all the factors. Alright, check your factors and see if they match mine. From here, now we're ready to see if we have any sets. According to the index, we need 3 of the same type of value. And notice, we do have a group of 2's that can come out. And we have another group of 2's that come out. In this case, we have removed everything from under the radical, so the radical disappears. And we are only left with 2 times 2, which we know is 4, and that would be your final answer. The fourth root of 4c squared times the fourth root of 12c cubed. This is your try it problem. Let's see how you did. Notice the index is the same, so you should have written it under a single radical, factored the values individually, reordered them, found your groups of 2 and c, and your final answer should have been 2c times the fourth root of 3c. Check your paper. If you do not have 4 as an index, you are wrong. Example 2, multiply. For a, we have the square root of 2 times 5 square root 3. Now this looks a little different. We're not just multiplying radicals. Now we have numbers or coefficients involved as well. What I want you to notice is the 5 is touching the square root 3. When items are touching, what operation is happening? Well, when things are touching, it means we are multiplying. So I'm going to put a multiplication symbol between those two. So what it looks like is we actually have 3 separate factors or values that are multiplying. And if you're a member of the commutative property, it means we're allowed to rearrange and write these in any way that we want. And that's what we're going to do. We're going to take the time to reorder. So any number that is not under a radical needs to go in front, and the radicals will go at the back. So when we rewrite it, it turns into a 5 times square root 2 times square root 3. Now that we've kind of sorted what's a radical, what's not a radical, now we want to simplify the values. The numbers outside the radical is just a 5. But the square root 2 and square root 3, since they have the same index and we're being asked to multiply, we can actually multiply them and write it as a single radical. Now that we've written it under a radical, we want to see if we have any sets. Lucky for us, 2 and 3 cannot factor because they're already prime. But for us to pull out sets, we have to have a pair of the same values. And in this case, we do not. So we go ahead and multiply the values under the radical, and we have 5 square root 6. And that would be your final answer. For b, we have 3 square root 7 times 5 square root 2. Again, notice the 3 and the square root 7 are touching, so I'm going to write a times symbol between them. And the 5 square root 2 are also touching, which means there is multiplication going on as well. So in this case, we have 4 different values that are multiplying, and we can reorder them according to the commutative property. So I want to take the values that are not under a radical and put them in front, which means I now have 3 times 5, and now I have square root 7 times square root 2 at the back end. Now I want to multiply what I can. In front, we have 3 times 5. We know 3 times 5 is 15. And the radicals, because they have the same index, can live under a single radical as 7 times 2. Now looking under the radical, we want to see if we can simplify and pull out any sets. Notice there are no sets to be pulled out, so our final answer is 15 square root 14. C, we have negative 9 square root 2, parenthesis 3 square root 2. Now this one looks a little different in that we do not clearly see a multiplication symbol, but there is one, because the negative 9 square root 2 is touching the parenthesis that does imply multiplication. Now looking from left to right, we notice negative 9 is touching square root 2. Well, that means multiplication. And as we just said, negative 9 square root 2 touching the parenthesis also means multiplication. And then inside the parenthesis, we have 3 square root 2, which is also multiplication. So we have 4 values that are multiplying, so we do need to take the time to reorder them. We move the values that are not under the radical to the front, which gives us negative 9 times 3. And then at the back end, we have square root 2 times square root 2. From here, we want to multiply the values. Negative 9 times 3 is negative 27. And the square root 2 times square root 2, because they have the same index, can be written under a single radical. From here we want to look under the radical and see if we can pull out any sets. Notice you do have a set of 2's that can come out. So we now have negative 27 times 2. The radical disappears because we took everything out from underneath it. And we know negative 27 times 2 is negative 54. And that would be your final answer. I think it's time to do a try it problem. So here we go. Your try it problem is negative 4 square root 7 times 6 square root 3. Let's see how you did. First, you should have rewritten it in terms of multiplication, reordered the values, multiplied them, and you should have come up with negative 24 square root 21. Example 3. A. We have the square root of 2, parenthesis, 5 square root 3 plus 3 square root 7, close parenthesis. This one's a little different. It's the first problem that actually involves a plus or minus sign. So what I want you to notice is look inside the parentheses. How many terms do you see? Well, it turns out we have 2 terms. And we will need to distribute to each of those terms. So the first term is 5 square root 3, and the second term is 3 square root 7. So this is a distributive property problem. The value that needs to be distributed is the square root 2. So let's distribute. Square root 2 times 5 square root 3. Next we have square root 2 times 3 square root 7. So notice we have 2 branches. That means we now have 2 terms. And we want to multiply and simplify each of the terms. The first term is square root 2, 5 square root 3. So again, a term consists of each of these values that are all multiplying, meaning we can reorder them any way that we want. So any values not under the radical need to be brought to the front, and those that are under the radical, as long as they have the same index, can be written as a single radical. So the first term can be written as 5 square root 2 times 3. The second term can be written as 3 square root 2 times 7. Now that we have each of the terms simplified, we want to look under the radicals and see if we have any sets. The first term does not, so we multiply and we have 5 square root 6. The second term we look under the radical. Notice we have no sets, so that becomes 3 square root 14. Now that we have simplified each of the terms, now we look at the problem as a whole. We're being asked to add these 2 radicals. Are these like radicals? Well, remember, like radicals have the same index and the same radicand. And these are not like radicals. So this would be your final answer. B, I have parenthesis square root 3 minus 5 square root 2, close parenthesis, open parenthesis, 2 square root 3 plus square root 2, close parenthesis. In this case, we have a binomial times a binomial. So we will need to distribute to each term. Looking at our first term, we distribute square root 3 to 2 square root 3. Then we distribute square root 3 to square root 2. Now we are done distributing the square root 3, and we move to the other term. This term is not 5 square root 2, but instead it is a negative 5 square root 2 times 2 square root 3. And again, negative 5 square root 2 times square root 2. So notice we have 4 branches. That means we have 4 terms. So now we are going to simplify each of these terms. Your first term of square root 3 to square root 3, we are going to reorder it. Any values outside the radical go in front, and then radicals can be grouped together if they have the same index. They can be written together under the same radical. So we can write the first term as 2 square root 3 times 3. The second term has no numbers outside the radical, but the 2 and 3 can be joined together in 1. The third term has a -5 and a 2 outside the radical, so that gives us -10, and the 2 and 3 can live together under a single radical. The last term has a -5 outside the radical, and the 2 and 2 can be together under the radical. Now that we have each of the terms sort of simplified, we keep going back to look for more. The first term, now we want to see, can we pull out any sets? And notice you can. You have a set of 3's, and so you have 2 times 3, and the radical goes away because you've pulled everything out of it. The second term, do you have any sets? No. So we write it as the square root of 6. The next term, do you have any sets? No. So we write it as -10 square root 6. For the last term, do you have any sets? Yes. So we write that as -5 times 2, and since we pulled everything out of the radical disappears. Now we need to clean this up a bit. 2 times 3 is 6. There's nothing we can do with square root 6 or -10 square root 6, and then we know -5 times 2 is -10. So each of the terms individually have been simplified. So now we look at the problem as a whole. We're being asked to add and subtract like terms and like radicals. Do we have any like terms? Well, notice 6 is a constant. Do I have any other constants? Yes. So 6 minus 10 gives us -4. Now we look for radicals. A square root 6 and a -10 square root 6 can combine. To what value? Well, it simplifies to a -9 square root 6. Remember, the square root 6 has an imaginary 1 in front of it, so 1 minus 10 is where that -9 is coming from. And this would be your final answer. C, we have parenthesis, 4 square root 2 plus square root 11, close parenthesis, all raised to the second power. Now, anytime something is raised to a second power, what does that really mean? Well, it means you need to write it out twice. This really means 4 square root 2 plus square root 11 times 4 square root 2 plus square root 11. So this really is a binomial times a binomial, which means we do need to distribute to each term. So again, we start to carefully multiply. Your first value is 4 square root 2 times 4 square root 2. Next we have 4 square root 2 times square root 11. Next we have square root 11 times 4 square root 2. And then square root 11 times square root 11. So we have 4 branches. We have 4 different sets of terms. Let's simplify each term. The first term, 4 times 4 is 16, and the 2's can be written under a single radical. The second term, we only have a 4 outside the radical. The 2 and 11 can be joined under a single radical. The next term only has a 4 outside the radical, and the 11 and 2 can be joined together. And the last one, there's no numbers outside the radical, but the 11's can be written under a single. So now that everything is grouped up and reordered, now we want to see if we have any sets. The first term, notice, we do have a set of 2's, so we can rewrite that as 16 times 2. The second term, we do not have any sets, so we can multiply 2 times 11 under the radical. The next term has no sets, so we can multiply those values under the radical. The last term does have a set, so we pull that out, which gives you an 11. From here, we want to clean up any values that we can. And notice 16 times 2 is 32, but everything else remains the same. From here, we have done everything that we can to each of the individual terms. Now we're looking at the problem as a whole, and we're being asked to add these different values. So we need to combine any like terms or like radicals. Our first value is a 32, which is a constant. Do we have any other constants? Yes. So 32 plus 11 is 43. Next we have 4 square root 22. Since we have a radical, we want to find any other square root 22's. And we have one. So if we combine that, that gives us positive 8 square root 22. And since these are not like terms, this would be your final answer.